the ZK Black Pill with Uma from Succinct. In this episode, we talk more in depth about zero-knowledge cryptography and the ZK circuits inside the pill. The Black Pill is if ZKvms are here and they can prove everything, did we just waste years of infra development and funding and time on optimistic rollups, custom ZK circuits, and restaking? More on that on this episode of Macrocosm. Okay, so quick intro, quick overview so we can get into the more deeper stuff. Who you are, what is Succinct, what is SP1, high-level overview. Go for it.
Hi, I'm Uma. I'm one of the co-founders of Succinct. We're building this ZKVM called SP1, where developers now can just write normal code, so normal Rust code, to use ZK. And we think the future of all ZK stuff will be through ZKVMs like SP1. And it's useful for building things like ZK rollups, ZK bridges, and basically anything in blockchain that needs to use ZK, and also outside of blockchain.
Mm-hmm. So the first question is, so typically when ZK is explained, they have the sort of key in the cave analogy. They have the Where's Waldo analogy, the two colored pencils, you put them behind your back. And they explain the zero knowledge property, like what zero knowledge is, but are those accurate representations on actually how ZK works with the math side? Typically, they just kind of say there's magical math and like they kind of go over it. Is there any like easy way to understand the math side of it, or yeah?
I do think those analogies that are pretty simplified. So compared to like what we do for proving realistic computations, like a roll-up state transition function or something more complex. I think depending on like what level of detail you want to get into the math, there are like simpler explanations and then more complicated stuff. Like if you want to understand this cryptographic security proofs, that's going to just be a lot of deep math, probably at like the PhD level. But if you want to get like a high level of understanding, I think Vitalik has some pretty good blog posts that probably if you've done like an undergrad degree in math, you can like read and understand the basics of what's going on.
Oh yeah. And I guess let's now get into ZK circuits. So what are ZK circuits? And then we'll get more into like SP1 stuff.
Yeah, so ZK circuits are are kind of like the old way that people used to do ZK. So a circuit is basically like you take a computation you want to prove, and then you break it down into like a really simplified form. So you break it down into basically additions and multiplications. And you can kind of think of like in your computer, there's a circuit that when you're running anything on your computer, at the end of the day, it gets, compiled down and run with zeros and ones and bits, because that's kind of the language of computers. In ZK world, things get broken down into polynomials, and we break things down into additions and multiplications, roughly speaking. And so that's kind of like how the ZK, that is the old way of doing ZK, where people would take some complex computation, break it down into additions and multiplications, and then you would do like all the polynomial stuff on top and generate a proof.
Mm-hmm. Could you talk on, I think before we get into SP1, sort of why inherently these proofs are like really hard to make and require like really beefy machines? Could you just explain that property?
Yeah. So when you try to do a ZK proof, it generally involves a lot of overhead. So you're taking your computation, you're breaking it down into these like statements about polynomials, and then you do like a bunch of stuff with those polynomials. And generally the computations you do on top of those polynomials to generate a proof are really computationally expensive. You're doing like FFTs, you're doing a lot of hashing, you're just doing like a lot more work. And the reward for all that work is at the end, you get this proof where now anyone can verify it for much, much cheaper than doing the original computation. So it's kind of like you put the work up front, but then you get like instant verifiability for everyone in the world, and they don't have to redo it.
Mm-hmm. So my understanding is that you sort of draw this polynomial on a chart, and then you have other people, then you ask someone else, to put a whole bunch of dots, and if the dots fit on this polynomial line, then you can like understand that it's verifiable. Is that like the correct way to think about it? And that's why like you have to like check multiple of these points if they match the polynomial. Is that correct?
I think there's like some aspects of the ZK proving that use that property, which is what you said, which is like if you generally if you have a bunch of points on a polynomial curve, it's easy to check if a new point is like on that curve or not. Um, so that's like one aspect of the protocol, but then there's a bunch of other stuff that happens behind the scenes. But yeah, that's like one ingredient.
Oh yeah, because I hear that ZK proofs are not actually proofs. They just prove that you know it, but not exactly directly prove. It's like I heard it was probably not incorrect. Is what was that analogy for ZK? I forgot what it's called.
Yeah, it's a probabilistic proof. So it's basically like with extremely high probability, like, you know, 1/2 to the 100. So that's like the bits of security. You know you can you know like the statement that you're trying to prove, and you haven't generated a fake proof. It's kind of similar to like when you sign something, like a digital signature. So like you sign something with your private key. Um, that's also a probabilistic proof where theoretically if someone like was able to guess your private key or something like that, they could also generate a signature, but the probability of them doing that is really, really low. So it's kind of like similar to digital signatures.
Mm-hmm. My question is that if it's like high computation and if it's probabilistic, let's say instead of like the like 1 to whatever exponent, could you like go an exponent lower and like increase more efficiency, more like less computation, but like still have a ridiculously high probability of it being correct and like secure, but like way less computation. Is that possible?
If you reduce the bits of security, it can still be pretty secure and you can do less computation, but generally like um, the scaling isn't so if I reduce the bits of security to the point where CK proving is really cheap and like not, not that computationally expensive, then it's not that secure anymore. So it's kind of like you have to put in the work to get it to be secure, to be meaningful.
Mm-hmm. I guess now let's talk about SP1. So SP1 is a ZKVM, but it is a ZK circuit which is designed to build ZK circuits, or which is the best way to think about it?
Yeah, so SP1's pretty different from the circuit model. Like historically, if you're a developer, you have to take your computation, you have to break it down to adds and multiplies. It's like very primitive. It's like writing assembly, and then you could prove it. With SP1, you write normal code, and then it gets compiled to this RISC-V ISA. There's this like instruction set called RISC-V, and your program just gets compiled to just like a normal program. And then we prove the execution of RISC-V code with any program. So we basically prove like, hey, if I have a program and it has these instructions, when I run through it step by step, first do an add instruction, then the next instruction is like a subtraction or, whatever. Then at the end, it produces this answer. So that's like how to think about it. To take a deeper dive, we have a circuit that proves the execution of the RISC-V instructions, and then we can run any RISC-V program with it.
Mm. I think before we get into the like why ZKVMs are cool, can you talk about like the experience building circuits? Because originally, just like the origin story of Succinct, why Succinct was made, you guys were building circuits. Tell us that whole story.
Yeah, so when Succinct started, we were building ZK bridging. So we were taking this particular application of ZK, which is making secure interoperability between different chains, and we were writing circuits for that computation. And that really sucked because we had, taking these very complex computations and breaking them down to adds and multiplies was very, very difficult. It took a really long time. It was not that maintainable. So overall, it was just very bad. And then we, so that experience was what inspired us to build a ZKVM. We were like, this isn't sustainable. ZK as a space is not going to make it if everyone has to be writing circuits. Our dream is that we just write normal code and it just works. And then based on that, we were like, oh, we want to build a ZKVM.
Mm-hmm. Could you talk a little bit about the bridge that you guys were building, and then we'll talk about sort of how you guys proved Tendermint very quickly. So like what type of bridge, the development time, how many engineers, how much money, like all of that.
Yeah, so we first built an Ethereum-like client to bridge between Ethereum and Gnosis Chain, which is like another L1 that's also based on like Ethereum's consensus protocol. Um, so we wrote that in this circuit language called Circom, and then we wrote a Tendermint-like client in Plonky 2, which is this other circuit DSL. And both of those projects probably took several engineers, several months of time. And it was, pretty expensive to audit. Yeah, and very, very hard to maintain because like no one in the world knows how to write these like obscure DSLs and circuits. Yeah, so with the ZKVM, it was pretty magical because, for example, for making the Ethereum-like client, we took an existing Rust Ethereum-like client called Helios, and then we were able to take that and run it in SP1. And actually, our intern did that project in like a week or something like that and got it running end to end. And that was a project that I'd personally worked on in the circuit world that had taken me many, many months. So that was like a really magical moment where we're like, oh, SP1 and ZKVMs accelerate development timelines by, probably 100x. Similar story with Tendermint. So our original Tendermint-like client was like thousands of lines of code. It was, took months to develop. It was really hard to maintain. And our SP1 Tendermint-like client is 300 lines of code. It's super simple. And, it took like a few days to put together, if that. So, and that was because we're able to use the existing Rust Tendermint library and just stick it in SP1 in like 300 lines of code.
Yeah, that was really, really cool. Could you talk about the experience of building SP1? Because you still have to like do all that circuit stuff, ZK stuff, but generalize it. Could you just talk about that process?
Um, so when we build SP1, like building SP1 is really, really complicated. We like our team has to build circuits. We have to put everything together. It's a pretty complicated process, and overall, it's a really complex system to build. Building a ZKVM is honestly really hard, but then our developers don't have to worry about that. All they have to worry about is like writing normal code. But yeah, building SP1, took us a long time, and even a lot of our experiences with writing circuits kind of like compounded into having the knowledge to build something like SP1. And so we like borrowed a lot of our earlier work in building all these circuits and kind of took that knowledge and put it into making SP1 as fast as it is today.
Yeah. Could you also talk about the idea that like if you spend more time making an efficient ZKVM, it's actually faster than custom ZK circuits from a proving time, like not like faster as in the time it takes to build a circuit, but like just the compute. Like just talk about that whole idea.
Um, yeah, so it's actually really interesting that a lot of the things we prove with ZKVMs are faster than custom circuits people write for them. And that's kind of counterintuitive because it's those people are designing custom hand-built code for their computation. In our ZKVM world, you're just throwing it into Rust and proving it. And it, it's much more general purpose tool. So it's kind of like, why is this faster? Because it should have a lot more overhead. But in practice, what we find is that actually SP1 can be faster than many of the custom circuit stuff because um, of all the engineering work that our team does into optimizing it. And just to give a really concrete example, with SP1, we put a lot of engineering effort into making a GPU prover for it. And the reason for that is that GPUs, they're just able to do a lot more compute per like dollar amount of like electricity, and they're also just a lot faster end to end. And because SP1 is such a general platform that you can have so many different applications built on top, it's very easy to like, you know, justify the engineering effort to make a GPU prover for it. Whereas if you have a special circuit for a specific computation, it's not worth like the many months of engineering effort to make a GPU prover for that particular instance because only one use case benefits. Whereas with SP1, every time we improve its performance by 10%, like there's so many people, there's probably like hundreds of developers and hundreds of applications whose lives get better. And so because there's such a broad platform, the engineering ROI is much higher for any individual optimization. And that all stacks together to make the system way, way more optimized than having these individual silos.
Mm-hmm. Another question is, so currently it's just you plug in Rust code. Could you have other code as well, or like talk about, could there be a Go ZK circuit or ZKVM, I mean?
Yeah, so we are able to prove the execution of any code that gets compiled to RISC-V. And Go can also be compiled to RISC-V, but there's like some technical difficulties with compiling to like our variant of RISC-V. So in the future, I think we don't support Go right now, but I think in the future we definitely could.
Okay. I thought it was Rust specific, and then you have to like write another, so it compiles all the way down to RISC-V. I guess now let's talk about usage of SP1. So do you have any sort of examples? I hear Celestia is going to enshrine sort of a ZKVM, and then you talk about like the more applications and use cases and like all that stuff.
Yeah, so I think ZK is just critical to scaling all blockchains. Like I think blockchains are just not going to scale and be verifiable without ZK. And so I think one day every user transaction is going to involve a ZK proof at some point, where like either you're submitting your transaction to a ZK rollup and then a bunch of transactions get aggregated together and then ZK proven, or even like there's talks about like Ethereum L1 being snarkified with the ZKVM. And certainly like teams like Celestia really need ZK because their execution layer in L1 is super minimal. Um, so in terms of like the use cases we see today, probably the most popular one is rollups. So we recently launched this product called OP Succinct, which basically allows any OP stack rollup to turn into a full ZK rollup by taking Rust code of its state transition function and then sticking that in SP1, running it, and making a ZK rollup. And there's been a lot of demand from that for that because I think a lot of rollups want to be ZK rollups. There's a lot of clear benefits. Like you can get to stage one quicker and easier. You can, instead of being a multi-sig, you can have fast finality of 1 hour instead of 7 days. So I think the end game is like all rollups are going to be ZK rollups, and people know and love the OP stack. They use it a lot already, and OP Succinct lets them just take their existing rollup and turn it into a ZK rollup very, very quickly.
Yeah, let's talk about that idea for OP Succinct. So, do you agree with like the infra black pill that is like everything that is deterministic code will just be like ZKified and just proven up front? Because like OP stack was like the optimistic rollup, and like now like in a couple of weeks they just slapped on ZK, and like all of that optimistic work is essentially like worthless now, is like the real answer. So do you think that ZK will just eat everything up, and sort of this optimistic stuff and like restaking is sort of no longer as valuable as it was?
In short, yeah. I agree with what you're saying. Yeah, I think, look, the rollups deployed a few years ago and they went to market fast. And back then, it's true, the ZK technology wasn't ready. It was too slow, it was too expensive, and worst of all, it was just too hard to build the ZK rollup. Like you'd have to have a full team of cryptographers, and even then, it was like a years long journey to deploy these systems into production. Now with the ZKVM like SP1, you can just take your existing code and then it slots in really nicely. You just take your existing rollup stack. You can keep everything. You can keep your entire rollup framework. You just implement the state transition function in Rust, which already a lot of teams have done because like Rust is pretty awesome. A lot of developers like it. It's very performant. You stick that in SP1, you prove it, and you integrate it into your protocol. So it's really simple. It's like kind of I like to joke that it's almost a weekend project to now use ZK. And so now it's like, okay, the tech is finally ready. It's easy, it's cheap, it's actually easy to use as a developer, it's maintainable, it doesn't slow down your team. So yeah, I think it's like time that everyone start using it everywhere it should be.
Yeah, there were a lot of ZK projects that built their own circuits. Sort of, I think ZK Sync, Polygon, Scroll, like just like a whole bunch of ZK projects. And now that's sort of commodified is the best way to say it. Uh, what do you think about the branding towards ZK? Because like ZK Sync was like ZK is the end game, and now it's like no longer really their circuit. It's no longer their version of ZK. It's no longer Polygon's ZKVM. So just like, yeah, talk about that.
Yeah, I think well, I think they were right that ZK is the end game, or they are right about that. So I actually really agree with them, and I respect all their teams like a lot. I think the Polygon team's awesome, the ZK Sync team's really awesome. They've done a lot of amazing work. I think for a lot of those teams, like I actually think today people talk about being a ZK rollup team, but I think that's actually wrong. I think there are rollup teams and then there's ZK teams, but being a rollup team today just means like you have to focus on getting applications and like getting liquidity and getting users and on ramps and off ramps. And the truth is, for building a rollup is just so much harder than the ZK stuff. Like building your rollup protocol, building a really high uptime sequencer, building all the bridging stuff, um, and building your community. Like that is really, really difficult work. And like, I mean, honestly, maybe in some ways that's like more difficult than all the math stuff we're doing, like building your community, getting the applications, onboarding institutions, whatever. So I think every rollup team will use ZK, and like the existing ZK rollup teams should just view themselves as rollup teams. Like they're going to be rollup teams. They will have ZK rollups. It can be either through their in-house stack or it can be through a ZKVM. But ultimately, like to their users, it doesn't really matter, right? It's just like they interface with the rollup team. Their main product's the rollup, and like what you do behind the scenes to get the security and like get the ZK stuff probably isn't like super important.
Yeah, no, definitely agree. Could you now talk about the proving time and sort of how I don't really understand how the, I guess, computation works from the idea of if you write more code, it takes more longer. Is it more exponentially longer if you have more code to prove it? And there's a flat proving or flat verification, I guess, time, or like talk about the proving time, all the code stuff. I really don't understand it at all. Or
Yeah, so the longer your program is, that's not usually related to the amount of code. Like, for example, you can write a really short program like Fibonacci and then be like, I want to compute the 10 trillionth Fibonacci number. And that'd be a really short amount of code, but it would be a very, very long computation. So, yeah, the longer your computation, the more time it takes to prove. Generally, it's like it scales linearly with the amount of computation you do. So, behind the scenes, like there's this concept known as cycles. Basically, like how many RISC-V instructions does your program take to execute? And a program that takes 2 million cycles to execute will take twice as long, roughly speaking, as a program that takes 1 million cycles to execute. But it's not exponential scaling; it's linear.
okay, and so whenever you're proving a block, is it better to prove per block? Is it better to batch? Is it better to prove a block and then include that proof inside another one? Sort of just talk about proving times and proofs.
Yeah, if I'm trying to prove, I mean, that really depends what you're optimizing for. So And yeah, this can get like pretty complex. Generally, there's like kind of a sweet spot of cycle count we find where like for just as a ballpark for us today with our SP1 precompile system, proving an Ethereum block is like roughly 300 million cycles. And that's like a pretty good number for our system. We generally prove stuff that's like in the hundreds of millions, low billions of cycles. When you start getting to like, 50 billion or 100 billion cycles, we can prove those programs. Like basically, we are able to prove programs of arbitrary length because we decompose them into like smaller chunks and then we recurse them into like one final Stark. So we have this argument for like proving an arbitrarily long program. So we can do it. It's just like it takes a really long time to do because you're proving this really big monolithic program. Whereas if you decompose it into smaller ones, you could like prove more of them in parallel, and it kind of has better properties. Yeah, I mean this is like a complex topic, and oftentimes the teams we work with, we like talk with them and work with them to figure out like, oh, how should you like design your program?
Okay. To be honest, I'm pretty satisfied with all the answers. Is there anything I missed? Any misconceptions? Anything else before we wrap it up?
Yeah, maybe one thing to talk about is like why SP1 is so fast. I think that's like something that it's actually a pretty simple topic to understand. And I think it's like a fun one to dive into.
Yeah, let's go for it.
So, um, yeah, basically, like one thing we realized from the start of building SP1 is that most workloads people care about improving, like rollups, like clients, that kind of stuff. Generally, in all these blockchain workloads, they spend most of their time in like cryptographic operations, like hash functions, signature verification, stuff like that, like SHA, Ketchak, those kinds of things. And those hash functions and cryptographic operations are really, really expensive in RISC-V. Like they take up the grand majority of the cycles. And so we realized that it would be a really powerful unlock if we could have specialized circuits for just those operations that could be like used by our ZKVM. And we call that notion precompiles. So it's pretty similar to like Ethereum precompiles, where you call a precompile contract and it's a lot faster than doing the same thing in Solidity. And we built that system for SP1 from day one. And that was a really big reason that SP1 is kind of an order of magnitude faster than other ZKVMs for things like proving an Ethereum block. So we have precompiles today for like Ketchak, the hash function, SHA, elliptic curve operations. And in the end, what ends up happening is that you can basically reduce the amount of work you need to do by like 10x because you're using these specialized circuits for those operations. And that's kind of what leads to SP1 being 10x faster for proving an Ethereum block or other things like that today, which is, I think, pretty awesome and kind of like foundational to letting us do things like OP Succinct, where we have to prove like a lot of roll-up blocks and their performance and cost is really critical.
Mm-hmm. That actually opens up another question. Is that so? The reason why GPUs are faster than CPUs is because they're just way bigger and allow for more parallelization. Could you have multiple GPUs work on one proof? Is that like a possibility, or you need it all in one giant system?
No, today we already parallelize proving across many GPUs in our kind of production cluster. So yeah, that's something we already do actually. And it results in like the end-to-end latency being really, really fast for proving.
Yeah, that I didn't know that. Wow. Anyways, I think I'm pretty much satisfied. You answered all my ZK questions. Thank you so much for hopping on. And do I want to shout out something at the end or anything like that?
Yeah, I think in terms of the things to check out, you can always like get started with their docs. It is actually really easy. Like you just go to docs.succinct.xyz and you write Rust and it works. It's kind of magical. And then yeah, if you're building a rollup, I think OP Succinct, which is kind of our solution to making any rollup a ZK rollup in like a very reasonable, sane, cheap, cost-effective way, is also great to check out. So yeah,
Okay, thank you.
yeah, thanks for having me.